Welcome to the session on algebraic methods, mathematical proof. The objectives for this session are to understand what constitutes a sound mathematical proof, use appropriate techniques to prove mathematical statements, and prove mathematical identities. Let's begin with some vocabulary. A theorem is a proven statement, and a conjecture is a statement which requires proof. Now, a proof is a structured and logical argument to show a conjecture is always true. A proof will start with theorems, works through a series of logical steps, with a final step in the proof as a statement of what must be proven. So let's look at some practical steps. A mathematical statement can be proven true by deduction. We begin with some known facts or theorems. Then, using clear logical steps, we arrive at the statement of proof. So, for example, we state that the product of two odd numbers is odd. An example of this might be that 3 times 11 is 33. 3 is odd and 11 is odd, and of course the resulting 33 is also odd. However, how do we prove this more generally? Let's prove this statement. Now, two odd numbers m and n can be expressed as follows. M equals 2p plus 1 and n equals 2q plus 1, where p and q are integers. So if we multiply m by n, we obtain 2p plus 1 times 2q plus 1. Let's expand the right-hand side to give 4pq plus 2p plus 2q plus 1. We can factorize part of this to denote the even number part of this number. So 4pq plus 2p plus 2q can be expressed as 2 times, and in brackets, 2pq plus p plus q. And of course we have a 1 tagged on at the end. And therefore we can conclude that the product of two odd numbers is an odd number, since this number is an even number plus 1. What is also important in a mathematical proof? A mathematical proof must state any assumptions being used, show each step of the proof clearly, each step must follow logically from the last step, ensure all cases are covered, include a statement of proof at the end. Let's take a look at an exercise. Show that a minus b times a plus b is identical to a squared minus b squared. Pause the video and have a go. Press play when you're ready to view the solution. Now, to prove a mathematical identity, we need to start with one side of the identity, so either the left-hand side or the right-hand side. Then we manipulate the expression algebraically until it matches the other side. So let's prove exercise 1. The left-hand side is equal to a minus b times a plus b. Let's multiply this out to give a squared plus ab minus ab minus b squared. Now let's tidy up. ab minus ab becomes 0, so we're left with a squared minus b squared, as shown. And this, of course, equals the right-hand side. Have a go at another exercise. Prove that 2x minus 1 times x minus 2 times x plus 3 is identical to 2x cubed plus x squared minus 13x plus 6. Again, pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. We're going to begin with the left-hand side again because it's easier to expand and cancel. So let's multiply out the brackets. We multiply out the last two brackets first, as shown. And then multiply out the rest. And finally, we tidy up. And of course, once we've tidied up, we can see that this is equal to the right-hand side of the identity that we were required to prove. As shown. And therefore we can conclude that the identity is true. Have a go at another exercise. Prove that if x minus p is a factor of f of x, then f of p equals 0. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve this. If x minus p is a factor of f of x, then we can express f of x as x minus p times g of x, which is another polynomial. Now, if we plug in x equals p into this, we obtain f of p equals p minus p times g of p. So here's x equals p plugged in. Therefore, f of p equals 0 times g of p, which equals 0 as required. Let's have a go at another exercise. Given that x plus 2 is a factor of f of x equals 4x cubed plus 5x squared plus a, find the value of a. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. If we substitute x equals minus 2 in f of x, let's see what we obtain. F of minus 2 equals 4 times minus 2 cubed plus 5 times minus 2 squared plus a. And this equals 0, since we know that x minus minus 2 is a factor of f of x. Hence, if we tidy up, we obtain that a equals 12. Let's now have a look at some geometrical results. A diagram can be very useful if you are trying to prove a geometrical result. Let's take a look at another exercise. Prove that a equals 3, 1, b equals 1, 2, and c equals 2, 4 are the vertices of a right-angled triangle. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. We produce a sketch of the triangle to help with the proof. Here it is. The gradient of AB is equal to change in y over change in x. So gradient of AB equals 2 minus 1, as shown, over 1 minus 3, which equals minus a half, as shown. The gradient of BC, again, equals change in y over change in x, which is 4 minus 2 over 2 minus 1, which equals 2. And the gradient of AC, again, is change in y over change in x, which is 4 minus 1 over 2 minus 3, which equals minus 3. So here are the gradients of the three lines AB, BC, and AC. Now, since the gradients are different, all the points are not collinear and therefore form a triangle. Notice that the gradient of AB times the gradient of BC is equal to minus half times 2, which is equal to minus 1. Why do you think this minus 1 is special? Recall that when we want to prove that two lines are perpendicular to one another, we're required to prove that their gradients multiply together to give minus 1. And therefore, AB is perpendicular to BC, and the triangle is a right-angled triangle. And therefore, we've proved the statement of exercise 5. Let's have a go at another exercise. The equation kx squared plus 5kx plus 3 equals 0 has no real roots. Prove that k satisfies the inequality 0 is less than or equal to k is less than 12 over 25. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. Now, since our quadratic has no real roots, b squared minus 4ac is less than 0 in our conventional notation. Therefore, 5k all squared minus 4 times k times 3 is less than 0. And therefore, if we tidy up on the left-hand side, we obtain 25k squared minus 12k is less than 0. This implies that k times 25k minus 12 is less than 0, since we've factorized the left-hand side. Let's sketch this, substituting x for k. The graph shows that 25k squared minus 12k is less than 0 when k is between 0 and 12 over 25, as shown. We will consider the case k equals 0 separately. If k does equal 0, then what happens? We obtain 0 times x squared plus 5 times 0x plus 3 equals 0, which implies that 3 equals 0. Clearly this is impossible, and therefore there are no real roots at k equal to 0. And therefore the equation has no real roots when 0 is less than or equal to k is less than 12 over 25. And therefore we've proved exercise 6. This brings us to the end of this session. If you have understood its contents, you should be able to understand what constitutes a sound mathematical proof. use appropriate techniques to prove mathematical statements, and prove mathematical identities. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.